In section 2.2, we want to formalize the idea of the limit of a function, a concept that we talked about briefly in 2.1 when we considered the tangent and velocity problems. So just kind of looking at that definition, we say that the limit of a function f of x as x approaches a certain number a is going to equal some value L. And what we mean by that, this notation means the limit, again, is going to be L of a function f as x goes to a. We mean that we can make the function f of x as close as we want to that value L by taking x values that are close enough to the value of a. In other words, we can get as close as we want. You want to get within 1/10, 1/100th, 1/1000th. We can get as close as we want to that value for f of x as long as we let x get closer and closer and closer and sufficiently close to the value of a. Now notice that we never said that x is equal to a. In fact, we're only looking at values where x does not equal a. When we look at limits, we're really not interested, well, in theory, we're not interested in what the value of the function is actually at a. What we're interested in is what the value of the function is when x gets closer and closer to a, for numbers that are very close to a. But again, we're not really considering the value of the function at that point a. To illustrate this, let's look at some graphs. For example, let's say we're looking at this graph of a function y equals f of x. And let's suppose that we're looking at our a value to be 1 here, and we want to find the limit as x approaches that a value of 1 of our function f of x. Well, here what we're going to do is we're going to consider values of x as we approach a and get close to it from either side. And what happens to our function value? Well, as I come at it from the right side here, you can see my function value is getting closer and closer and closer to 3. Whereas I come at it from the left side here, you can see my function value is getting closer and closer and closer also to 3. So it appears graphically here that we can make our function come out to be as close as we want to 3 by taking our x values to be sufficiently close to the value a. Now that's going to be true, and it is true that the limit of this function as x approaches 1 is equal to 3. And you can see that, because the actual point 1 comma 3 is on our graph. So we have the point 1 comma 3 that's on our graph. And so if the function is continuous at that point where x is equal to a, well then the limit of the function as x approaches a is going to be equal to the function value. In other words, if the function goes through the point and it's continuous there's no holes or gaps or anything, well then the limit of the function as it approaches that x value, in this case a equals 1, will be equal to the function value at that point. But it doesn't have to be the case. If we have a function g of x where we removed this point right here and replaced it, say, with an open spot here, so the function is undefined at that point. So if we have a function here, g of x is, well, let's say it this way. Let's say it has the same values as the original function f of x as long as our x value is not equal to 3, but it's undefined when x is equal to 3. And we wanted to look at the limit. Let's make those x values 1. We want to have the function f of x when x is not equal to 1. So it's the same curve here as long as x does not equal 1, and then undefined when our x value is equal to 1. That's why we have that little hole right there. Now if we look at the limit here of g of x as x approaches 1, what do we get? Well, again, we can make our function g in this case as close as we want to 3 as long as we make our x values sufficiently close to 1. And so the limit here is also 3. So let's look at an example here. Let's suppose we have the function f of x and it's equal to x squared minus 2x minus 3 divided by x plus 1. Well, you can see that this function is undefined when x is equal to negative 1. If we put negative 1 in for x, we're going to get some value on top, but we're going to get 0 in our denominator. So the function is undefined at x equals negative 1, but that does not mean that we can't take the limit as x approaches negative 1 of the function f of x. And the way we're going to do that basically is we're going to look at the values of the function as we get closer and closer to negative 1 and see what the function approaches. So if we look at a few values here, we can just make a table, x and f of x. That'll allow us to help find the limit. So let's just try some values close to negative 1, such as, negative 0.9, negative 0.99. Let's come at it from the other side as well, negative 1.1, negative 1.01. So these are values close to negative 1 that are a little bit to the right of it on the number line. These second values are close to negative 1, which are a little bit to the left of it on the number line. Now, if we put these into our calculator and just take f of these values, hopefully we'll see something that's getting closer to a number. And if I put negative 0.9 in, what I got is a negative 3.9. Let's try negative 0.99. And here I got negative 3.99. It looks like it's getting closer to 4. Let's check values that are to the left of negative 1 on the number line, a little bit farther to the left, a little more negative. Let's first start with negative 1.1. And when I do that, I get negative 4.1. How about negative 1.01? Well, here I get negative 4.01. So it looks like as our values get closer and closer to negative 1, the function value is getting closer and closer to negative 4. Now again, we can't actually plug negative 1 into our function and evaluate it because our function is undefined at negative 1. We have to take the limit by looking at values of x that are getting closer and closer to negative 1. And we could keep going. We could take negative 1.001 or 0.999 and get closer and closer to negative 1. But what we're going to see in this case is that the function values get closer and closer to negative 4. So we will guess then that the limit as x approaches negative 1 is in fact negative 4. Now we're going to look at methods we can use to actually verify this in 2.3, but at this point, based on the evidence that we have, we would say the limit of our function as x approaches negative 1 is negative 4. Let's see if we can verify this graphically. If we put the function in that we looked at, we had x squared minus 2x minus 3 divided by the quantity of x plus 1, and let's see if the graph also illustrates that the function approaches negative 4 as x approaches negative 1. Well, here's the graph here. Notice that it looks just like a straight line, and we'll see why that is in a second. It looks just like a straight line. But what you see here is as the function x approaches negative 1, the function value does approach negative 1, 2, 3, 4 right here. And also look, if you can see here, there's a little hole at this point. See if I can zoom in on it. Now it kind of disappeared, but there was, in the last picture you can see there was a hole at negative 1, negative 4. And so the way these computer graphics work, a lot of times they put the hole in, a lot of times they can't because of the way that they plot the functions. But we know that the function is undefined when x is equal to negative 1, and the graph of this thing is actually this line with the hole right here at x equals negative 1. The reason for that is, if you look at our function, if you look at x squared minus 2x minus 3, that factors into x plus 1 and x minus 3 all over x plus 1. So it does simplify into just the line x minus 3, which is exactly the graph we're looking at, a line with a slope of x, a slope of 1 rather, and a y-intercept of 0, negative 3. But the original function itself we have to consider, and that original function says that we can't put negative 1 into it. So what we end up with the line x minus 3 only undefined at that point, negative 1. But the limit of that function is exactly what you would get if you put negative 1 in for this linear function. Negative 1 minus 3 is negative 4. Alright, then some other problems in your book discuss what happens if you choose different values. Sometimes the calculator, if you choose the right values, or I should say the wrong values, can give you limits that don't actually exist, or misleading limits. So you want to look at those. But next thing I want to talk about are the concept of one-sided limits. So we have this notation here. The limit as x approaches a with a little negative sign above the a. We read that as the limit as x approaches a from the left. So x approaches a from the left of f of x is equal to L. And what that means is, just like the previous definition of the limit, this means we can make the function f of x as close as we want to this limit value L by letting x be sufficiently close to a but less than a. So x approaches a from the left means our x values that we're going to be looking at are going to be only x values that are less than a. Now we can do a similar definition and look at the limit as x approaches a from the right, if we put a little plus sign, of f of x equals L. So here we would just change our definition to, instead of x less than a, we would say x is greater than a. We can get our function to get as close as we want to that limiting value L by taking our x values to be sufficiently close to a, but only taking those x values to be bigger than a. And so we see then that the limit itself of f of x as x approaches a in general, the first type of limit we talked about, as x comes to a from either direction, is going to be equal to some value L, and that's going to be true if and only if the one-sided limits are also equal to L. If and only if the limit as x approaches a from the left of our function is equal to L, and the limit as x approaches a from the right of our function is equal to L. So we can only have an overall limit if the one-sided limits from both sides exist and agree. Let's look at an example. Let's take a look at number 4 out of your book, where we're asked to find several limits, some one-sided limits and some just limits in general for this function f of x, as you can see in the graph here. Now notice that the function is defined everywhere. It's defined at every point for x. But notice that when x is equal to 3, we have a jump, we have a gap in our function. The function value jumps from what was going to be 4 down to 3, and then after it goes to the right of 3, it jumps down to 2 and beyond there. So let's look at our limits here. The first one, part A, we're looking at the limit as x approaches 0 of the function in general, of f of x. Well, as x approaches 0, that's going to be this point right here, and as we come at that from the right and come at that from the left, our function values are getting closer and closer to 3. So that's equal to 3. Now, it's also true in this case that f of x, or f of 0, does equal 3, so the function is defined there. So the value of the function is equal to the limit. I should say the function is continuous there, which makes the value of the function equal to the limit at that point. But you can see as we come at it from the left or the right, the function value approaches a height of 3. Let's look at part B. Part B, we're looking at the limit as x approaches 3 from the left of our function f of x. So now we're only allowed to look at x values that are less than 3. So we're only allowed to approach it from this left side here. As we come into the left side, the function value gets closer and closer to 4. And so that's all we need to see. The limit as x approaches 3 from the left is 4. We can get this thing to be as close as we want to 4, the function value, as long as we take x values as close as we want to 3, sufficiently close to 3, to the left of 3. How about part C, where we come at it from the other side, the limit as x approaches 3 from the right of f of x? Well, as we come at x, or come at 3 from the right here, our function value is getting closer and closer to 2. So the limit of f of x as x approaches 3 from the right is equal to 2. A couple more here to look at. How about part D, where we take the limit as x approaches 3 in general of f of x? Well, since the limit from the left and the limit from the right don't agree, we have to say that the limit of f of x in general is not defined. So we can't get our function to be sufficient, or to get arbitrarily close to a particular value, because we get it close to different values depending on whether we come from the left or the right. If we come from the left, our function gets close to 4. If we come from the right, our function gets close to 2. So the limit of f of x as x approaches 3 is in fact undefined. Now compare that with the fact that in part E, we do recognize that f of 3 itself is actually equal to 3. Our function evaluated at 3 is equal to 3. So the limit is undefined, even though our function does exist at that point, is defined at that point. Probably actually a better way to say it, instead of saying it's undefined, we usually say that it does not exist. That limit does not exist, again, because the limits from the left and from the right, the one-sided limits, do not agree. Okay, that's a good place to stop for this first lecture. We'll look at a few more examples in the second lecture.